we'll get started anyway from the current slide. Now, if you remember, the slide set for this chapter, or this section, was a few verbiage slides, one example slide, and that was it. Okay, whereas the section has bunches of examples, and so we're doing all the other examples on this first slide. Let me get the pen set up for it. All right, we got it coming in. I think we did down through example 4. Were there any questions before we get started today? Okay, here's example 4. This is on page, it would be on 359, okay? Section 5.2, example 4, near the bottom of the page. Here's an identity, tangent x plus cotangent x. The question is this really equal to EJ being here? And I guess it is. We'll see. Anyway, all right. Is this equal to secant x times cosecant x? All right. Now, how would you approach a problem like that? We're trying to determine if that identity is indeed true. That's called verifying the identity. They claim it's an identity. We got to determine if it's true or not.
Do you put it in terms of sine and cosine?
Absolutely. That's the title for the thing, and that's exactly what you do. There's no squares in it, so Pythagorean identities aren't going to help you. So when all else fails, get it in the sines and cosines. So you tell me. Let's start with tangent. What's that in terms of sines and cosines? That's sine x over cosine x. What is tangent? Cotangent. Cosine x over sine x. Now, the book doesn't usually like to do this. I do. What is secant x? One of those reciprocal identities. Which one? One over what? Cosine x, okay. And cosecant is? 1 over sine x. Okay, we got everything in terms of sine and cosine. Now, remember, you can't cross the equal sign. You can do things on both sides, but don't ever carry something over, okay? So, which side looks like to you to be the one that requires the most work? Left or right? Left, because you got sum of two fractions here, you got the product of two fractions. Anyone can do that, that's pretty easy. This one, what you got to do? It's sort of like that, but not quite. Cross multiplying usually is crossing an equal sign. We don't want to do that. But I think what you're saying is right. We find the least common denominator, which is, well, I'll take it in 2 steps. Okay. What's the least common denominator between cosine and sine? Second? No, let's see. If I say what's the least common denominator between 2 and 3? 2 won't go into 3, 3 won't go into 2. Huh? 6, yeah. It's a bigger, so don't think least means the smallest you can do, but of all the common denominators, it's the least one. So what would this be? How did you get 6 out of 2 and 3? Multiply them. Well, guess what we'll do here? Multiply them. So this will be sine x times cosine x. Sine x times cosine x. Okay? Because sine will go into both of those, cosine will go into both of those. Okay. Now you started out with a cosine in the denominator. What did you do here to get a sine? Multiply. So guess what you got to do in the, yeah, you got to multiply on top to get that too. Sine times sine would be, second? Okay, how you went from cosine to sine times cosine, you multiply by sine. If you multiply the denominator by sine, you must also multiply the numerator by sine, and that would give you what? Sine squared. Very good. Sine squared x. And over here, you would multiply by cosine, and that gives you cosine. I can't write. Let me see if I can clean that up a little. Okay. Okay. That gives you cosine squared x. Now the question is that the same as, let's just write this as 1 over cosine x sine x. We will do that to the right-hand side, so it's simple. Well, you got the two common denominators. That means keep the denominator, sine x, cosine x, and combine the numerators. What does that give you? Plus cosine squared x. Okay? And what's sine squared plus cosine squared? Second? What's sine squared x plus cosine squared x? Plus cosine squared x. What would that be? 1! That's your Pythagorean identity, isn't it? The basic 1. So this is just 1. So guess what you got? You confirm the identity. Because the numerator there is 1, the denominator is sine x cosine x, which is the same as cosine x sine x. Sure enough, those are the same. Right? Now they actually change them back to be secant x, cosecant x. Why? Save yourself a little effort there. Okay, there's also a checkpoint at the bottom. Well worth doing the checkpoint. All right. Now, in my pre-calculus algebra class, it was just before this one, we were looking at complex numbers, just a quick review of them, overview of them, or something like that. And one thing, when we found out we went to divide by them, what's the technique we use to divide by a complex number? Does anyone remember? All right, Chavette is here. Increase the class size by 50%. Okay. And I don't know if you went there Friday, did you? Oh, okay.
It's over there, man.
Is that all you needed?
Yes, for the other.
All right. Glad to. I was starting to leave it with the secretary. I said no, because I was already well past 1. Yeah. I said if you haven't come by now and you don't come, then I'll wind up seeing you on Tuesday, but having it over there, so I brought it with me. So, okay. Good deal. All right. Chevette's here. I got your mark. Okay. My question was, I don't know if y'all remember how to do this, but when you're dividing by irrational numbers, like the square root of 3 plus the square root of 5, how do you divide by something like that? You multiply by its, not reciprocal, conjugate. Yeah, that one. And in complex numbers, you multiply by the complex conjugate. So, believe it or not, when you're dealing with trig identities, there are sometimes you use the concept of a conjugate. Now, what is a conjugate? That's, for example, if you have 1 over 1 minus cosine x. Now, I don't know really how to simplify that very much. It's not a regular identity. It's not a Pythagorean identity. It's not a reciprocal identity. You know, what do you do?
And you have to multiply by 1 plus cosine.
Very good. Let's try it. It's usually worth a shot. Multiply by its conjugate, which would be 1 plus cosine x. Okay? But if you do that to the denominator, guess what? Got to do it to the numerator as well. Okay? So I messed up my numerator. I made it more complicated. 1 plus cosine x. But now the denominator is what? Cosine squared x. And guess what that is? Right? What does it become with the Pythagorean identity? What's 1 minus cosine squared? No. There's your 1. Okay. Now you just did it before you came in. What was your Pythagorean identity you're trying to use? The most common one. Okay, sine squared x plus cosine squared x is always equal to 1. So to get this to look like that, let's subtract the cosine x, sine squared x from both sides. And what do you have? These go away. You have sine squared x is equal to 1 minus cosine squared x. Well, that's what your denominator is, 1 minus cosine squared x. So what does it become? 1 plus cosine x over, what is 1 minus cosine squared x? Sine squared x. Now, here's how this is better than what we had to begin with. It looks a little more complicated, but here you had a binomial in the denominator, which is hard to mess with. When you have a binomial in the numerator, we can just split that into 2 different fractions, right? So this would be 1 over sine squared x plus cosine over sine squared x. Okay? Now, what is 1 over sine squared? Reciprocal identity. Which one? Look it up if you need to. What's 1 over sine squared? It's 1 over sine. Help out somebody. Say again? I think it's, oh.
350.
You can give me the answer too. Yes, you do. We've already done it at least once today. 1 over sine is? Cosecant. So, and since it's squared, that would be cosecant squared. X plus, now this takes a little more work, but not much. Let's split this into 2 fractions. Cosine x over sine x times 1 over sine x. Okay? And what would that be? I'm going to go up here with it. That would be cosecant squared from the first one plus, and what's cosine over sine? Call this cotangent x, right? And what's 1 over sine? That's cosecant x. Okay? Now that's a perfectly good answer. Okay? That's it. Yeah. You could factor out cosecant cosecant if you wanted to. It's not necessary. and leave you cosecant x plus cotangent x. But I don't see how that's really much simpler. Okay. Either one of those are perfectly legitimate. So you go from having a sort of a simple looking thing here, but it has a denominator. And if you want no denominators, you go to something that's not that complicated looking, but at least it has no denominators. Okay? Now, they left it in yet another form. They left it as cosecant squared times 1 plus cosine. Okay? Which is a good form too. They stopped right here and made it 1 over sine squared would be cosecant squared times 1 plus cosine x. Now, that to me it's a fine form too. All those are correct answers. Which leads me to my little soapbox, which is why I do not like the computerized packages, which, just because computers are dumb, I mean, you might think they're really smart things. They really aren't. They only recognize one answer. Where here we have 3 totally correct forms for the same thing. No one of those is any better or any worse than the others. Perfectly fine. So, if you had this on a computerized thing like WebAssign or something like that, if you put 2 out of the 3 of those, they'd probably count it wrong, but it'd be perfectly right. The other one, they happen to have programmed in to be the right answer, so they'll say, yes, that's right. Okay? So I really don't like those, because then you'll spend all your time, what did I do wrong? You did nothing wrong. You got it right. It just doesn't recognize it's the right answer. Okay? What's that? I just saw that was ugly, so I wanted to clear it up. Okay. All 3 of those are correct answers. All right. Now, that leads to, very directly to, example 5. Like I was saying before, if you remember from last time, this section in the slide set had maybe 2 or 3 slides on descriptions, introduction, that kind of stuff. And then one example, that one example you see there, after it did that example, that was all. Even though there are several examples in here. We're getting ready to start example 5. It's not on the slide set, so we're doing it here. Verify this identity. Secant x plus tangent x supposedly is equal to, we don't know for sure though, cosine x over 1 minus sine x. Okay? Now, what might you suggest that we do to verify that identity? Any ideas? Okay, wait just a second. I just saw something I didn't like here, so I'm going to clean it up just a bit. Okay, and Elijah's trying to get marked here twice today. Okay. EJ, sorry. What did you say? Sorry, Shavette.
Do the right side first, get the fraction.
Okay, you certainly can do that. I don't mind doing both sides at once, remember? What could you do the left-hand side? That's your cue. Same thing you suggested on the last one.
You did the last one?
Yeah.
And turn the sign back.
Ah, I like that. Clever, you thought of it. Okay. So, what is secant x? 1 over cosine x. Plus, what's tangent x? Well, that's 1, but get it in terms of, what did you tell me? Sine and cosine. Cotangent isn't a sine or a cosine. What's that in terms of sines and cosine? Huh?
Sine over cosine.
Yes, sine x over cosine x. Okay. Now, what would you suggest we do to the right-hand side? Shavette wanted to do something. What was that? Say again. By what? The what?
1 plus.
Yes, 1 plus sine x. That's the conjugate. Okay? But if we multiply the denominator by that, what have we also got to do? Numerator by 1 plus sine x2. Why do we have to do that? What is 1 plus sine x over 1 plus sine x? 1! And when can we multiply by 1? Anytime you want to, because it doesn't change the value in it. It just changes the way it looks. All right, so what does that new... Let's start with the denominator. What does that new denominator become? 1 minus sine squared x. We'll come back to that in a minute. Our new numerator, we're going to leave just like we have it. Cosine x times 1 plus sine x. Okay. Well, what is that? Okay. Let's go back to the left-hand side. What can we do with that? Guess what? Yes, add the numerator because you already got a common denominator, don't you? So that'll be a 1 plus sine x over cosine x. I like it. Okay? Fairly simple, concise, yeah. Okay, how about that right-hand side? Look, we already got a 1 plus sine x. I'm hoping we hang on to that. No reason not to. But what is that about that denominator? That looks vaguely familiar. What's that?
Squared.
What's squared?
In the denominator.
What about it?
Can have a square in the denominator.
You can. Really? I missed that rule. Okay. What Pythagorean identity is it? It's a slightly different form because when you have squares, look for Pythagorean identities. Okay, say that again. Sine squared x, is that what you said? Plus cosine squared x is equal to 1. Okay, can we rearrange that to make it look like that denominator?
Yeah.
Subtract the sine squared x from both sides. Right? These go out, and what do you have left? Cosine squared x is equal to 1 minus sine squared x. And guess what that is? That's our denominator. So what we could replace that 1 minus sine squared x with? All right. Here's Orlandria. Okay. Okay, we almost have half the class here. Hopefully we'll get some more. What's our new denominator there? You told me, but Cosine squared x, right, okay. Okay, now what can we do? What's that? You've got a factor of cosine x up here, and this is cosine x times cosine x, so wipe out one of those and you get cosine x, and guess what you got? Left-hand side equals the right-hand side. See it? So you've done it. No longer is it a question mark. We know that's true. Right? Some stuff confusing you, or which one?
How do you explain that this verifies that the answer is?
That what? This?
That's verifying the top?
Okay, no. You try to get this side equal to that side.
Oh. Okay.
Yeah, as long as all the steps you do are fair and square and time square, no, okay, all the way down, and all these steps are fair and all accounted for, if you can get these two to equal each other, you've shown the identity is true. Oh, that thing doesn't look at all like what we started with, okay? But when you do enough steps, you can get them to be the same. Just don't cross the equal sign with doing any of these things. Do each side independent of the other. Make sense? All right. That was example 5. Let's move along to... Now they're going to work with each side separately. Guess what? We've been doing that, okay? So I'm going to clear all this off, and we'll do example 6. Cotangent squared x divided by 1 plus cosecant x is equal to, or supposedly is equal to, 1 minus sine. Oh, I'm sorry, these aren't x's, these are thetas. Okay. It doesn't really matter what you call the thing, but since the book called them thetas, I'll call them thetas. Let's see, 1 minus sine theta over sine theta. Okay. Where would you suggest we begin? And how would you suggest we begin?
Well, we gotta get rid of both of the denominators, right?
Possibly. Remember, we can have things in the denominator as long as they're the same. But they're not quite the same yet. Now, if you were going to, I'm taking from your question, you're thinking of how to get rid of this denominator at least. And how would you do that? Conjugate? That is a good idea. That numerator is going to get fairly complicated then, but that's okay. We can deal with complicated, okay, I think. In fact, that may be a very reasonable complication. But remember, sort of one of the first things is, see if there's anything you can do to simplify, and what does cotangent squared bring to mind? So I got Pythagorean identity, and which one would that be? 1 plus cotangent squared. Hear that. Let me write it down while you're saying 1 plus cotangent squared theta is equal to cosecant squared theta. Okay? Which means to get the cotangent by itself, I'd have to subtract the 1 from both sides, right? So this goes away and you get cotangent squared theta is equal to cosecant squared theta minus 1. Do you buy that? Yeah, so another way of that same Pythagorean identity. So that at least gets you cosecants here. So this will be cosecant squared theta minus 1 over 1 plus cosecant theta. Now, you've done something to the left-hand side. Now, they're suggesting we do something to the right-hand side as well. And here's what I suggest, okay? Again, you have a binomial in the numerator, a monomial in the denominator, so why don't you split this fraction into 2 fractions, right? Now that's getting away from signs, but it may not be a bad idea. So this would be 1 over sine theta, right? Minus sine theta over sine theta, right? And what's sine theta over sine theta? 1. So that's a 1, okay? Now, anything special about this entity here? That numerator. That's a difference from 2 perfect squares. So couldn't you factor that out? Say again? Cosecant plus 1 times cosecant minus 1, right? Sum and difference of their square roots. So let's write this as cosecant theta cosecant theta plus 1 times cosecant theta minus 1 over, now I'm going to rearrange the denominator. Is that legal? Because it's just an addition. Whoops. I'll rewrite this as, yuck, I can't write this. Cosecant theta plus 1. Okay? And guess what? These go away, don't they? Now, let's go back to the left-hand side. I mean, right-hand side. What's 1 over sine theta? Say again? 1 over sine theta? Cosecant theta. Cosecant theta. I can't write that for some reason. And then we said the other was minus 1. And guess what we've got? The left-hand side is equal to the right. I know that's an ugly cosecant theta, but that's what it is. I just have trouble writing cosecant. I don't know why. Okay, let me try it again. Cosecant theta. Still not very pretty. Okay. But your left-hand side is equal to the right-hand side. Now, these two are 1. This is 1. This is equal to that. Oh my goodness. Now that's one way of doing it. Is that the way the book did? Oh my goodness.
They did like I was saying at first.
Yeah, they did the first step just like we did, and then they factored just like we did, and that gave us that. And then on the right hand, yeah, they did it the same way we did. They just did them separately rather than side by side. And sure enough, those are equal. Okay. Any questions? Folks, get to know these identities. You know how you get to know them? How do you get to know your friends? Spend time with them, don't you? Share things with them. Work on problems together. That's how you get to know them, okay? I'm really a little suspicious. Maybe not enough homework problems are being done because y'all seem like they're strangers. They're not real good friends yet, okay? Try to get to know them. All right. All right, to erase this, or y'all still working on it? Huh? Okay? All right. Example 7, which I think may be the last one in the section. Okay? Ooh, yes, these were fun, weren't they? Verify each identity. There's 2 parts here, so we'll drag this out as long as possible. And by the way, there was a checkpoint after that last one, too. Good thing to go home and practice with. Get to know them. So here's one that's tangent to the 4th power x. Is that the same as tangent squared x times secant squared x minus tangent squared x? Oh my goodness. What would you do to that? Where would you start? Second? Okay, breaking up is hard to do. No, never mind. What? The left side? The tangent 4th? Yeah, you could do that, but does the right-hand side look a little more complicated? Why don't we factor that one? What can we factor out of those 2 terms? Tangent squared x. Yeah, let's factor out a tangent squared x. And what are you left with? A secant squared x on this side minus what on the minus 1. Very good. Okay, does that look at all familiar? Where would you go to check? Secant squared x minus 1. Let's say? Okay. 1 plus tangent squared x, is that what you said? 1 plus tangent squared x is equal to what? Whoops. Started to write a theta. Isn't that equal to secant squared theta? I mean x. Okay. Is that your Pythagorean identity? 1 plus tangent squared x is equal to secant squared x. Got it? Okay. Now, here we have a secant squared x minus 1. So what would we do to that to make it look like that? What if you subtract 1 from both sides? Okay. Here the 1's go away. Okay. And you're left with tangent squared x, right? That's equal to secant squared x minus 1, right? So down here, instead of secant squared x minus 1, you can write tangent squared x. And guess what? What is tangent squared x times tangent squared x? Tangent fourth x. Bingo, it works. Oops, you can't say bingo in Alabama. Say again? You didn't have to. You could have started off by factoring that as tangent squared times tangent squared. Notice that tangent squared is secant squared minus 1, and then multiply through. Yeah, you could have done it that way. I just thought it was easier that way to do it. Both ways work, okay? In this case, I wouldn't get it in terms of sines and cosines because you just have all those squares and fourth powers and stuff. So use your Pythagorean identities to try to simplify things, and they work. Got a question about it?
I'm just seeing where you replace secant squared x minus 1 in parentheses with tangent squared x. You just, because they equal each other, you just.
Yeah, because those are equal to each other. Okay. Yeah. So instead of this, put the other side. They're the same. I can remember Miss Virginia Dozier, my high school algebra 1 teacher. She talked through her nose and she said, equals times equals equal equals. And equals plus equals equals equals. And equals minus equals equals equals. I got really sick of that. Really quick. But yeah, if they're equal, substitute it. Okay? Ready for the B part? No, we don't want to leave this section. It's been so much fun, but we got to someday. So let's do the B part. Here we have a cosecant to the fourth x times a cotangent x, and they say that's equal to a cosecant squared x times a cotangent x plus a cotangent to the third x. All right. Ew. Which one looks like it might most benefit from our doing something to it? To simplify it. Left side or right side? Let's deal with the right side. What would be one thing you could do to that right off the top? Let's just leave that cosecant squared alone for now. Now, of what remains, what might you do to it? Say again? Factor out what? You may have said it, I can't hear well. Cotangent x, right? And what's left after you factor that out? Of the first term, you have a 1 plus, in the second term, you have a cotangent squared x. Okay, two sets of parentheses there. In fact, I may do it like this and only use 1. I think that'll be a little better. Okay. Now, one reason I like that is we've wound up with a cotangent on both sides, and that's good. So let's try not to mess with that one. How about that 1 plus cotangent squared x? Any way to simplify that? And what Pythagorean identity would that be? Say again?
The sine squared x plus cosine squared x.
Okay, is that the only one?
Oh, that's cotangent. I thought it said cosine. Never mind.
That's the same as a cosecant squared right there, isn't it?
I thought it said cosine.
Okay, so this will be cosecant squared x times cotangent x times, and you said that was what? Cosecant squared x, right? And now what do we do? Multiply those two together, and what do you have? Cosecant to the fourth x times cotangent x. And guess what? That is exactly equal to that. So you have verified the identity. Goodness gracious. 10 is not cooperating at all. See how that works? Yeah, you just try to get the two sides to be the same. You really didn't have to do anything to the left. Working with the right, you got there.
Why you didn't do anything with the middle part, like, when you set the third row? Where's it? Yeah.
This one? Yeah, once you factor that out, I didn't want to do anything to it because you had a cotangent x here. Leave it alone. See if you can get everything else to get to be the same as that. And sure enough, we did. Right?
But why did you said you multiplied that cosecant squared x times that cosecant squared x.
Right.
But you didn't touch the middle part.
Because I didn't want to mess with that. I wanted this to become that, and sure enough, multiplying them makes them become that. Leave that alone, and you got it. What you want to get is the two to look alike, to be the same. And sure enough, that did it. So you don't have to do everything in the order that it shows up. Be selective. Multiplication is associative. You can, and commutative. You can flip them around, swap them around, do whatever you want it to, as long as it's legal. And guess what? There's 2 checkpoints with that one too, or A and B on a checkpoint. I would highly recommend doing that. Any questions on 5.2? Let's look at vocabulary. An equation that is true for all real values in its domain is called an blank. If you look at the title of 5.2, the last word, it's at the top of, Identity, you got it. Number 2, an equation that is true for only some values in its domain is called a blank blank. Very first page of the section. Conditional equation, you got it. Number 3, fill in the blank to complete the fundamental trigonometric identity. Hint, get to know them. Okay, what is 1 over cotangent u? Tangent u, very good. Number 4, what is cosine u over sine u? Say again? Cotangent u. What is sine squared u plus blank is equal to 1? Cosine squared u. Perfect. Number 6. Cosine of pi halves minus u is, a little louder. I can't hear you.
Secant.
No. Cosine of pi halves minus u. Sine u. Exactly. All right. Number 7. Cosecant of minus u is negative cosecant of u, because secant, like sine, are odd functions. So the cosecant of a negative would be the negative of the cosecant. And then secant of negative u would be secant u, because cosine and secants are even functions. Homework exercises, any of the odds 9 through 49. There's a whole passel of them there. Do some of each type. You know, if you get going and it looks really easy, skip over to some that look a little more difficult. Okay? Now, number 51, obviously they had some complaints about it, so they started doing describe the error. They put the big X, meaning that it's wrong. You find out why it's wrong. So try doing 51. Then do any of the odds 53 to 57, either 59 or 61 or both. Do 3, and then do 65. Not a bad idea to look at 67 and 69. Oh my word. 69 really looks bizarre, doesn't it? Oh, no, I'm sorry. It caught me as an optical illusion there, yeah. Do either of those true false to 67, 69. I would do both of them. Think about it. Do either 71 or 73. You don't have to, but I think that would be sort of fun to do. And that, I think, is the end of section 5.2. All right. So now we're going to go to 5.3, if I can get it to come up. There we go. Okay, 5.3. Goodness gracious, my head is clogging up. PowerPoint is slow. Here we go. All right. Continuing in analytic trigonometry, 5.3 is solving trigonometric equations. And you thought we were just doing the identities because they were fun. They were fun, but there's a bigger purpose in it, so we can solve trigonometric equations. So that's what we're going to do here. The objectives are using standard algebraic techniques to solve trigonometric equations. Now, how do we usually solve equations? Well, you solve for the unknown, you simplify, you factor. We'll do every technique we can think of. We'll solve trigonometric equations of the quadratic type. There's factoring really comes into play there. Solve trigonometric equations involving multiple angles. Ooh, okay, let's see what that happens with that. And we'll use inverse trigonometric functions to solve trigonometric equations, because guess what? When you're solving an equation, you usually do it for a variable. What we're going to do is solve for the function first, and then do the inverse to solve for the actual variable. So we'll do all of those. And the introduction here states that to solve a trigonometric equation, and these are conditional equations, by the way, not identities, we'll use the standard algebraic techniques when possible, such as collecting like terms, factoring, doing all the things we did with variables, we'll do with the trig functions. Your preliminary goal in solving a trigonometric equation is to isolate first the trig function on one side of the equation. Then we'll solve for the variable by doing an inverse. Okay? For example, to solve this equation, 2 sine x is equal to 1. Well, ultimately, we want to figure out what x is, but before we can do that, we need to figure out what sine x is. So what would we do? Trying to isolate the sine x, what would you do? Divide by 2. So that gives you sine x is equal to 1/2. Ha, we've isolated the sine function. Now, what value x that when you take the sine, what angle x when you take the sine of it, do you get 1/2 as an answer? Y'all know that. Yep. And I saw you drawing in the air. I will draw it on the board here. Okay. What I usually go to, how do we define sine? I like to use the x, y, and r form. So what would that be? Okay. Sine of, they're using a x already. Yuck. Let's make that sine theta. Okay. So we can use x, y, and r. What is sine? No, I think that's cosine theta. Y over r. Okay, right? So here we got r is equal to 2. That lets me know to tick off a circle here. That means make them angry. No, that's not what I meant. Okay, of radius 2, because that's your r. Okay, your y value is 1. So here's where y is 1, so we'll come over here and do this angle right here. That angle right there is going to be my theta. This is 1, that's 2. Y over r. Now, what angle is it that you have? What is this angle here, theta? So that the sine of it is opposite over hypotenuse, which is 1 over 2. What angle would that be? One of our favorites. Say again? Okay. Now I'm going to do something that's a bit obnoxious perhaps, but I'm going to bring this 1 down here too and do this triangle. Now we got a 1 here and a 1 there, so that makes that 2. This is 2, that's 2. What kind of triangle is that? If all 3 sides are the same, 2, 2, and 1 and 1 is 2, what do we call that? Say again? Called it. If sides are the same as lines, and lines sort of the same as the lateral, they're all equal, we call it equilateral triangle. All right, okay. And the equilateral, meaning equal sides, what does that tell you about the angles? They're equal too. Now, any triangle, the 3 side angles are going to add to 180, right? Any triangle, the 3 sides add to 180. And if all 3 of them are equal, each of those is. You like writing on the air. I have to erase the air after you leave every day. Okay. 60. Okay, so each one of these angles is 60. There's a 60, there's a 60, and there's a 60. Right? Now, we doubled this, so this angle here that we're really interested in is half of 60, which is 30. Okay, so in degrees is 30. What would that be in radians? Okay, do it this way. Okay, what is? Okay, you're talking about, yeah. Okay, let's go back to this. The equilateral triangle. Pi what? Pi half? I don't think so. Pi half is 90. Remember?
Oh, it's pi.
Pi what?
Is it pi?
Pi is 180. Okay. Which leads me to pi equal 180. What are the 3 angles in the triangle add to in radians? Pi 6. You're absolutely right. pi 6. 30 degrees is pi 6. Or like I was just going to say, if these three angles add to 180, that means in radians they add to pi, right? And you got three angles equal to pi, 3 theta equal pi, each one is pi thirds. And then half of that is pi 6. Okay. So lots of ways to get there. But so down here we see the x is equal to pi 6. Okay. Possibly. Okay. It could be plus 2n pi. Remember, it could be any multiple of pi 6. But that isn't the only place, because sine is also positive over here. So if that was our angle and this was also pi 6, this would have been 5 pi 6, right? So it could have been or 5 pi 6 plus 2n pi. So you have a whole bunch of things that could be, but one of those would be, the simplest would be pi 6, or 5 pi 6, or any 2n multiple of 5 pi 6. Okay. They didn't carry it that far, I don't think. They were just using that as an example. Oh, no, they did, didn't they? Okay, let's just see. Yep, they did. They did pi 6 and 5 pi 6. Here's a pi 6. And here's a 5 pi 6. But then, add 2 pi to that, or subtract 2 pi to that, or 5 pi 6, and add, subtract 2 pi, add 2 pi, so it's 2n pi. So, but if you're staying on the interval from 0 to pi, 2 pi, from here to here, then you only have these two values, pi 6 and 5 pi 6. Okay? If you're, the whole thing is pi 6 plus 2n pi plus 5 pi 6 plus 2n pi. Now they did it from the sine graph, which is a good place to do too, but I can't look at this and say, oh, that's pi 6 there. Yeah, I know that's exactly pi 6. I mean, not in my drawing, okay, but on the unit. I don't make it a unit circle, a 2 circle. That worked out pretty nicely. Okay. So, there we solve the equation. Now, they also do it on the, and this is their answer, which is exactly what we got. They also show it down here, which is what I did by doing, you're looking for the x, the angle, whose opposite side is 1 over the hypotenuse of 2. 1 over 2. And we knew that to be pi 6, but also over here, it's 1 over 2, so 5 pi 6 as well. And then if you keep going around in circles, you add 2n pi to each of those. Okay. That's all your coterminal angles with those two. When solving trigonometric equations, you should write your answer using exact values rather than decimal point approximations. So in other words, pi 6 is an exact answer, where if you put 0.5 dddd, that would be an approximate answer. So they like for you to put that, and then for all multiples of that plus 2n pi. 2n pi is an irrational number, but that says it all right there. 5 pi 6, same type thing. Okay. So here's example 1. What do you reckon we're going to do on this one? There's your example 1. What are we going to do? Say again? Okay, I hear you saying something, but my hearing's so bad. Add a sine x to both sides? I think that's a great idea. What you're trying to do is get all your trig functions on one side and the numbers on the other. So we'll first add sine x to both sides. Equals with equals. Okay. So this will be 2 sine x plus root 2. And when you add those together, you get 0. So obviously we got to do something else. And what's that? Get your numbers on the other side. So we'll subtract the root 2 from both sides. Okay. That will give me 2 sine x, these add to 0, is equal to minus root 2. Now what? Trying to isolate the sine x, so we're going to divide by 2. Okay, that wipes out the 2's here, and that gives me sine x is equal to negative the square root of 2 over 2. And again, they're using x's here. I wish they'd use thetas because I like to use x's for my x, y, r diagrams. So let me go to it and call that theta now. Okay? Does anyone think of what angle would have a sine of negative root 2 over 2? First question I would ask myself, let's say self, no, not that, sorry. I would say, where is sine negative? Where? No, it's not. Third or the fourth, third and fourth quadrant. So we got to have at least 2 answers, one in the third and one in the fourth. Now I go back to the question of where, at what angle is sine root 2 over 2? The sine of what angle is root 2 over 2? Okay, we'll do negative root 2 over 2, but I'm just wondering what will it be? What angle is related to the sine of what angle is root 2 over 2? Pi fourths, that's the key. And in the third quadrant, you just told me, okay, in the third quadrant, here I'll do a radius 2 again. So there's our circle, something like that. Pretty ugly circle. You're either in the third or the fourth quadrant, and at pi fourths, you split that quadrant exactly in half, or you split that quadrant exactly in half, right? Okay? So what will that first angle be? That one. Okay, except let's keep it in radians if possible. I believe you're right. Okay. 5 pi over 4. You're absolutely right. Because this is pi, isn't it? The straight line would be pi. And then you're another quarter pi, which would be 5/4 pi. Okay? So that will be 1. X equal 5 pi over 4 plus 2n pi, because it repeats itself every 2. How about the one over here? I'm going to do that in a different color. What color would you like? Red. Okay, we'll do red. Okay, this one right here would be which one? What would be the red angle? 7 pi fourths. 7 pi fourths plus 2n pi. Okay? Here's how I think about it rather than looking at a thing. I'd say all the way around would be 2 pi, right? But you're 1/4 pi short of that. So that would be 8/4 pi minus 1/4 pi is 7/4. Very good. There are your 2 answers, and it didn't say specifically which quadrant or anything else. There's your 2. In fact, it's an infinite number of solutions, but the ones between 0 and 2 pi are 5/4 pi or 7/4 pi, because the sign is negative in both of those. Root 2 over 2 are your quarter pi's. Yeah. And then every time around after that, it's another 2 pi. Or even in the opposite direction, that would be a negative 2 pi. Okay. So that's what we got. Let's see what they got. Okay. So let's erase all this and see what they did. Begin by isolating sin x on one side of the equation. And I like to always go with one which is the larger. That's a plus 1 here, a minus 1 there. Let's bring the minus to a plus, add it to both sides, and that makes it 2 sin x. Sin x plus root 2 is equal to 0. That's 2. Goodness gracious, they do it so strangely. Then they subtract the root 2 from these sides. Then they add these two together. Boy, they go around the ear to get to their nose, don't they? Is it that time already? Oh, how can it be? Okay? And anyway, that gives you 2 sin x equal negative root 2, sin equal negative root 2 over 2, and the interval of 2 pi, we'll find all solutions in 0 to 2 pi, 5/4 pi, 7/4 pi, plus 2n pi. All right, we will start next time with example 2. Okay? Now, let me give you a few homework exercises. If you have to go, it'll be on Screencast-O-Matic on YouTube. Try to do any of the odds 5 through 9. Okay? I think you can probably try some of the odds 11 through 23. Nah, let's just do 5 through 9 to begin with. In fact, now that I look at it, just do 5, okay? Just do 5. We'll pick up the rest of those later. Good deal. Glad y'all were here. Don't know where everybody else is. Taking spring break early or something, I don't know.